So I'm Joey, and yes, so my talk is titled Systematically Building Mixed Integer Programming Formulations Using JuMP and Julia. So my research is kind of broadly in the area of mixed integer programming. So I want to show you kind of a little bit of some of the stuff me and Juan Pablo have done over the past couple of years, but I want to specifically focus on where I think the computational tools that are available are especially relevant, right? So it's either because they allow this research to exist in the first place, I'll discuss later on, but also because it kind of interplays nicely with the modeling tools that are available and we can build out because of JuMP and the Julia ecosystem. So I want to start with a simple example problem. So this is something you might have seen before. It's the transportation problem, right? So the idea is you have, let's say, some natural gas, and you want to route it from a set of processing facilities to distribution centers, right? You have some network that connects them, and you want to do it in such a way that minimizes the actual cost of actually using the network, right? So in the standard version of this problem, you have a linear objective function, and everything works out nicely, right? This is a linear optimization problem. We can solve it efficiently. We're done, right? So I want to make it just maybe a little bit more realistic now. So now let's imagine that we have a concave objective function, right, for each one of the arcs. So what this would correspond to is an economy of scale. So as I use more of an arc, my unit cost will drop correspondingly. Right, so now this is not something I can easily write for you as a linear optimization problem. In particular, we have this nonconvex objective function. How do we think about solving this? So the way I want you to think about it here is in terms of what's called the graph of this function. Right? So we have some input variable x, we add some new output variable y, and the graph is just what you would normally draw on a piece of paper. Right? It kind of couples the two together. And the reason this object is useful is you can come back here. We have all these non-convex functions, and we just replace each one with some new variable y, and we add a whole bunch of new constraints here that just couple x and y together, say that they have to lie in these graph objects. Right, so I'm going to focus particularly on constraints that look a little bit something like this. Right, so we say that some of our decision variables have to lie in a non-convex set. So we want to think about building MIP formulations for things that look like this. And the general approach we're going to take here is we're going to try to write the constraint disjunctively. So now let's imagine that this concave functions we were working with, they're piecewise linear. Right? So they might look something like this. In this case, it's easy to write it as a union of simpler things. Right? So here I'm writing, I can write my piecewise linear function as a union over these line segments, S1 through S4. So in general, I'll try to write things as a union of polyhedra. And you notice here that this constraint, there's no natural integrality that appears here, right? So what I'm going to do is I'm going to add some new integer variables. Let's call them z. And the real work to do here is to build a formulation, right? So what is a formulation? We need some LP relaxation, which is a polyhedral region, in the space of my original variables and the space of these new variables, such that when I take it and impose integrality somehow on my new variables and then project them out, I recover my original set. So again, there's no natural integrality here. I'm kind of introducing it artificially to model this non-convex thing, right? And so what this means essentially is that it's not really determine what this formulation should look like or how these integer variables should enforce this non-convex constraint, right? There's a whole kind of space of possible formulations we could play around with. How do we choose which one we want to work with? And it turns out that actually choosing the right formulation oftentimes can be really, really important. So what I have here are a series of experiments I ran with transportation problems, or a variant of them, where we have bivariate piecewise linear functions that appear in the objective instead. Here, I have three existing kind of, I would say, generic formulation techniques, things that you can kind of throw at anything. And on the right here, I have some new formulation we were able to cook up that kind of take advantage of structure a bit more. And what I'm doing here is I'm just looking at different families of instances where I'm essentially increasing the size or the number of pieces on these piecewise linear functions. Right? So we're doing some type of scaling thing. And all I want to highlight here is just that when we get to this largest family here, the existing formulations really just kind of break down. They're not able to solve 50 out of 80 of the instances in 30 minutes or less. Whereas if you use this kind of weirder, more exotic formulation we'll see in a minute, it turns out you can actually solve all of them. It takes, on average, about 2 minutes. Right? So there really is something substantial to be gained here. But again, the formulation we're going to see is really weird. So how do we come up with it in the first place? Okay. So I want to now turn to a couple different ways we can think about trying to understand what will make a good formulation before we actually run experiments like this. Right? So things that we can look for that we know tend to correlate pretty strongly with good performance. So the first one is what's called strength. So you can kind of interpret this essentially how closely does my LP relaxation approximate this set that I actually want to model. So we have our graph here, and somehow we can look at this and say, okay, this is kind of maybe a weak formulation because it's not as tight as it possibly could be. Right? And the reason this is important is you throw this to your MIP solver, and you're using this relaxation to kind of produce good bounds. Here we're going to see gaps, essentially. We can look at this and say, okay, well, maybe this is a little bit better. This is what's called a sharp formulation. It kind of gives us the convex hull of the set that we actually care about. And it turns out you can actually do better. So there's something called an ideal formulation that we'll focus mostly on. And this is where you take a sharp formulation, and you also say when you look at the extreme points of the relaxation, they naturally will satisfy this inequality condition that you want. Right? So this is kind of the gold standard of what you would want in terms of the strength of the LP relaxation. So that's one way of assessing the quality of a formulation. Another would be the size, right? So at the end of the day, what I need for this relaxation is just a big system of linear inequalities. How many inequalities do I need? How many new integer variables did I have to add? Right? The bigger the formulation is, the slower it will solve in general. Right? So we would also like a small formulation if possible. And then you can look at other things as well that I'm not going to dwell on here, but maybe, right, so we're using a branch and bound algorithm. When I throw it to the MIP solver, how does this relaxation actually start to change? Right? So I just want to show you these to show that there are multiple ways that you can think of assessing the quality of a formulation. They will often be in conflict. How do we think about trying to design formulations that we can expect will work well in practice? Okay. So the first way, I would just call it an ad hoc approach. And by that I just mean maybe the standard way. You just sit down with a piece of paper and you try to reason out the logic yourself. Right? So I want to start with a simple example here. I'll call this the set max. So what's going on here is I have some d-dimensional input variables x, and I'm constraining x to be in a hyperrectangle. You can just think of it as a 0, 1 box. And then I have some other variable y that is just going to be equal to either some affine function of x or 0, or the maximum of the two. So what you can think of is there any chalk? Yeah. Right, so what I'm doing essentially is I'm modeling this hinge here. Right, so you can think of this as my affine function, and then if it goes negative, I'm just going to chop it off at 0. And the kind of the input to this hinge here is going to be some affine function that I've specified. And the reason that this is an interesting set is because it arises in deep learning, right? So you train a neural network using these ReLU activation units, these hinges that look like this, right? So you have all your data, you spend a bunch of time training your model. So what you're training is the W and the B here, getting those coefficients. And then if you want to do something with this, you want to throw in an optimization problem, you end up with a lot of sets that look like this that you kind of concatenate together in some way. Okay? And if you stare at this for a little bit, you can come up with what you might call a big M formulation. Right? Essentially what you're going to be doing is building a formulation for this and just plugging in your affine function in some way. But what we're doing really is we add some new binary variable z, 0, 1, and this is going to be some indicator as to whether this max value is going to be equal to the function value or 0. Okay? So it's ad hoc in the sense that you can kind of look at this logic and reason out what's going on here. But unfortunately, this formulation is not ideal, it's not sharp, it's not particularly strong, right? So we'll return to this later on and see how we can use computational tools to think about actually building a stronger formulation. But now I want to move to a second way to think about building formulations, a combinatorial framework for actually constructing them in the first place. So let's return to this univariate piecewise linear function here. Right? So remember we have these segments, S1 through S4. And the way I want to build the formulation is in terms of these breakpoints, V1 through V5. And the observation here is that if I pick some point on the graph of the function, I can equivalently write it as a convex combination of these breakpoints subject to what's called the SOS2 constraint on these convex multipliers lambda that I've added. Right? So you might have seen the SOS2 constraint before, but essentially what it says is that if you look at the support or the non-zeros, there's at most 2 of them, and they have to be adjacent on this ordering that I've set. And the reason you do that is to avoid things like this. I don't want to take a convex combination of V1 and V4. This point is not on the graph. It's not going to be a valid formulation. So what I've done here is you start with this disjunctive set or constraint here. Let's say X and Y lie in the graph, this union of the segments. And I've transformed it to this disjunctive constraint on these lambda variables, these convex multipliers. And this new constraint is much easier to work with. Each one of these alternatives is just going to be some base of the simplex. And that's really nice for a number of reasons, but one of them is that you can now think about building formulations for it combinatorially. So we have our piecewise linear function. I'm going to build what's called the conflict graph. So the nodes of the graph are going to be the breakpoints. And then I draw an edge between every pair that are not contained on a segment together. Right? So V1 and V4, there's no segment that contains the both of them, so I add an edge. And then I want to build a decomposition of this graph, what's called a biclete cover. So there's some number of levels. On each level, I have a set of blue nodes and a set of red nodes. And then I want to draw all the edges between the two. And then when I take the union over all these levels and all the edges, I want to get exactly the edge set for this graph. And it turns out that once you have this in hand, you can really easily read off a formulation for the thing that you actually care about. So these are what I called independent branching formulations. And they're actually really simple once you have this biclete cover. Right? So for each level, you have a binary variable and 2 constraints. And these together, they either say that some lambda variables are 0, are going to be set to 0, or some other set of lambda variables are going to be set to 0. So these formulations are really nice because they are ideal, so they're really strong. And also, if I can get this biclete cover small, then the size is also going to be small as well. Right? So I really can control kind of the quality of the formulation by trying to find a small biclete cover. And this is more kind of interesting when you go to more complex types of constraints. So this is a bivariate piecewise linear function. If you look at the domain, the 2-dimensional domain of the function, I've kind of chopped it up, I've triangulated it in this way. And this is where the stencil formulation I showed you at the beginning, where we can kind of think about it. Right? So what I've done here essentially is built a formulation heuristically, but built it in terms of this graph decomposition. Right, so I need to come up with what these different levels should look like, and you sit down with a piece of paper and you can come up with this. But in principle, what this is kind of saying is we have a well-stated optimization problem to actually find the smallest formulation in this family. Right? It is a combinatorial optimization problem to find the minimum biclete cover. So you can solve an optimization problem to find the best formulation, essentially. And this is, I would say, even more important when you're working with unstructured constraints, things that might look something like this, right? So this might arise in a robotics type application where you have some object, let's say a quadcopter, you want to navigate around some obstacles, right? I can't stare at this and maybe find what the best formulation might be, but you can still solve an optimization problem to find out. So there's I would say a simple MIP formulation to do this. And I've implemented this in a piecewise linear hop, which is a modeling language or a modeling extension to JuMP that I've built out for piecewise linear functions. And essentially what you can do is you can go back to this stencil formulation I showed you and start making it a little bit smaller. You're shaving off constant factors, essentially. It helps a little bit. But really what we're running into is that this MIP formulation is not actually a good MIP formulation, so it doesn't scale. So I would say one wish list I have here is a practical, efficient algorithm for computing this minimum biclete cover and a Julia implementation of that algorithm. Right? I think that would be really cool. Okay, so now let's move to a third way to build formulations, way to do it geometrically. So we're going to use what's called the embedding approach. So the idea here is you take your disjunctive set, and we need 2 sets of ingredients. The first is a family of sets. Let's call them TI, right? And you can just think of these as corresponding to each one of the alternatives, each one of the line segments here. And then the second ingredient is a set of codes, or just integer vectors. So I look at each segment and I just give it some distinct integer vector. And we're going to build what's called the embedding. Right? So what I do is I take each alternative, each segment, and I append the code to the end of it, and then I take the union over all of them. So I've somehow taken my original disjunctive constraint and embedded it in a higher dimensional space. And the reason that we would care about this is because if you can build the convex hull for this embedding object, you can immediately get an ideal formulation. Okay? So this is a geometric way to think about building strong formulations. So how do we get that convex hull? One way to do it is to use this characterization here. So this is in terms of spanning hyperplanes, right? So we have all these codes. I'm going to need to take some differences between some of the codes, essentially based on kind of adjacency relationships between the different alternatives, right? That's what's going on here, right? But the big point is that we just build up a set of directions, and I want to compute all the hyperplanes that are spanned by that set of directions. And if you do this, you can really quickly read off an ideal formulation whose size is equal to the number of variables equal to the number of components of the codes that I plugged in, and the number of constraints here is just going to be twice the number of hyperplanes that I needed. Right? So a small formulation happens when I can find a small number of spanning hyperplanes for my particular assignments. And you can do that to build you can use this result to build some really weird formulations. So here's one possible choice of codes. I'm going to use it for univariate piecewise linear functions. Right? And the observation here is just that this set of difference directions that I need to compute are going to be well behaved, which means these spanning hyperplanes are going to be well behaved. I can write them down. There's not too many of them. They're just the unit aligned directions. Right? So what does this formulation actually end up looking like? This is our univariate transportation problem. Remember, we have these Fij's that appear in the objective. I plug in my new formulation, and this is what you get. Right, so you can try to parse out what's going on here in the constraints. If you can figure out what's going on, let me know. I don't really understand them. The coefficients are weird. It's not even clear looking at this why this is a valid formulation, much less an ideal formulation. But it works, right? And so I think this is really where the modeling aspect is particularly important, because I don't want people to have to read my paper and understand it, then write this down, and then go write code to build this, to actually use it, right? It's much easier if you can build on top of JuMP an extension, let's say, where you can essentially hide all of this formulation magic in one line of code. So that's what's going on here. One line of code to write a JuMP model that looks more like this rather than this. Okay. So I want to add another item to my wish list here. The only real way I've been able to take advantage of this result is when I can compute these hyperplanes in closed form. Right? So it would be really nice to have an algorithm that can efficiently compute them and an implementation in Julia to play around with these different formulations. But at this point, I just want to take a step back. Right? The key kind of result here is this proposition that just says that if you can compute this convex hull object, you immediately get an ideal formulation. And so one way to compute this convex hull is with this guy. But it's not the only way. You could also just use Julia and the tools in Julia to build the convex hull yourself. Right? So Juan Pablo and Austin Herling have a nice example here that they call the tower puzzle. And so the idea is you have some type of rectangular grid, and you're assigning numbers, integers, to these elements in the grid. And those numbers somehow correspond to heights. And then you have some set of vision number constraints, essentially, that constrain how these things can go together, subject to some constraints on, all right, if I'm looking at this row or this column, I want to, like, the higher numbers will block the lower numbers behind it, and so on, right? So there's somewhat complex constraints. It's not really clear what a formulation or what the best formulation for these constraints might be. So what you could do, actually, is just use Julia to compute an ideal formulation for these different constraints. Right? So this is a snippet that I pulled out of some of JP's code, where we're using the Polyhedra package that Benoit in particular has done a lot of really great work on, others as well. Essentially what we're doing is we're computing the extreme points of, you can think of it as computing the extreme points of this embedding, and then just computing the convex hull here. And we're using the CDD library that's really actually quite good at this, right? And so what we're doing is we're computing this ideal formulation on the fly, and you can kind of compose them together, right? Because this is just one constraint of many. And the real kind of nice thing about this is that you can do this quickly, right? So this takes, what, like under a second? And you can run this for every constraint where you plug in the different data, right, for a particular instance, build a strong formulation, and then you kind of concatenate them all together, right, and go from there. And then I want to close by just showing how you can use these types of techniques here to actually build your intuition as to what a good formulation might look like, right? So what I have here is a code to build up. I mentioned that there's these generic formulation techniques. So this is one of the formulations I've written down here. So this formulation is nice because it's strong, it's ideal. It just might have too many variables. So what I'm going to do here is I'm going to build up this JuMP model with all these inequalities. And at the end here, I'm just going to project out all these additional variables that I don't want. And I want to look at what this convex hull object looks like. So I choose some data. I print it out. And this is what the convex hull looks like. Right? I have a bunch of inequalities. Right? So you can do this. This will work for one particular instance if you just want to solve one problem. Or you can also run it for a bunch of different data, stare at it for a while, and then at the end of it, you maybe hopefully get a theorem out of it, or proposition rather. Right? So this is an ideal formulation for this max unit that I showed you earlier, the one that arises in a trained neural network. So essentially what's going on here is we have this original big M formulation that I showed you. What was missing are these two families, two exponentially sized families of additional inequalities that you needed to kind of chop everything else off. And the way I was able to kind of understand what's going on here, actually, it's actually pretty similar to some of the stuff in your thesis. So that was one of the inspirations. But it was also staring at printouts like this for a while, trying to understand what's going on. And then you can write down something like this. So in conclusion, right, so the way that you actually choose to formulate something can be really important from a practical perspective, whether you're able to get an answer at all. And there's a bunch of different ways you can actually think about building different formulations. Right? I've shown you a couple, a combinatorial approach, a geometric approach, one that really is just throwing it in Julia, see what you get out of it. And again, I want to just close with a wish list. If anybody was particularly interested in these two mathematical problems, come talk to me afterwards. So thank you so much for listening. If you have any questions, let me know.